What up guys? Today I got a crazy video and it might be a long video because we're going to move from the one-dimensional Schrödinger equation to the three-dimensional one. We've worked with the one-dimensional Schrödinger equation the entire series of quantum mechanics here, but the three-dimensional one is cooler. It's what's going to give us information about the hydrogen atom. So we're going to start here today. So here's what I have here. One-dimensional Schrödinger equation summary. We have the time-dependent Schrödinger equation, which has a time partial derivative here. The wave function depends on time. And here you have the Hamiltonian operator, again, acting on the wave function. The wave function depends on time. You can split this equation up using separation of variables, and this will give you a time-dependent wave function, which would normally use the letter phi. This thing kind of looks like an exponential I energy time over h bar, I believe. We don't really look at it because most of the time in introductory quantum mechanics, we're looking at steady state solutions, so independent of time. But if you want to look at time, you can slap on that time wiggle factor, as Griffith says. But we also have the time-independent Schrödinger equation, which is what gets spit out once you do separation of variables. Here's the separation constant there, the energy. So we have the Hamiltonian operator. This is an operator that only includes a position derivative, no time derivatives, nothing like this. We have the wave function, which now only depends on x, and it is one dimension, so it only depends on one dimension. We have the energy, which is just an eigenvalue, just a number. And we have the wave function, again, only depending on x. If we move to the three-dimensional Schrödinger equation, you can again split up using separation of variables, the time and the position. And here what I've written is only the time-independent Schrödinger equation. So it looks identical. We just expand from one variable to three variables. And we generally call these x, y, z. Everything here looks the same, except we're going to expand the Hamiltonian operator because inside the Hamiltonian operator is some other stuff we have to work on, which changes when you move from one dimension to three. But I have a few checkpoints of what we're going to cover in this video. Here are the checkpoints. We have three. The first thing is, inside the Hamiltonian operator, we have the gradient operator. We actually have two of them. The gradient operator acting on the gradient operator acting on the wave function. So this is the gradient operator squared, or you can call this the Laplace or the Laplacian operator. It is this gradient operator squared. And this thing changes. In one dimension, the gradient operator was literally this. Or if it's the Laplace version, the thing we see in the Hamiltonian, it is the second order. When you move to three dimensions, this thing looks a little different, and we're actually going to solve the Schrödinger equation in polar or spherical coordinates because it is much better because the hydrogen atom has spherical symmetry, so it'll make things a bit more simple, even though before they become simple, it looks a bit more complicated. So this is checkpoint one. We're going to talk about this very briefly. Checkpoint two is actually getting the full three-variable Schrödinger equation. So here is the term in the beginning, that thing that's attached to the kinetic energy of the Hamiltonian operator. Here is the Laplace operator acting on the wave function. You can see it gets much more complicated. We're going to build up from this to this. And here we have the potential energy, which only depends on r, no time, again acting on the wave function. And on the other side we have energy acting on the wave function, which is the same thing we saw in the one-dimensional case. So what you see here is the Hamiltonian operator acting on the wave function side, and what you see on the other side of the equal sign is energy acting on this. So this is the three-dimensional version. We're going to build up to this. That's why this is checkpoint number two. Once you have that, you've successfully expanded the Schrödinger equation into three variables, into, in this case, theta, phi, and r, which are spherical coordinates. You can keep this in x, y, z, but like I said, the hydrogen atom, which is what we're going to use the three-dimensional Schrödinger equation to solve for, it has spherical symmetry. It's going to be much better working with it in spherical coordinates. But we're still not done yet. Checkpoint three is again using separation of variables here, which you were allowed to do, and getting three separate equations in different variables. We call these the radial equation. This one just depends on r, and this is where the energy and the potential energy are chilling. The other one is the polar. This depends on theta, and the other one is the azimuthal, which depends on phi. These two equations together you can solve for right away. I don't think we're going to do that in this video. We're going to maybe check that out in a next video. Moving from this equation to this down here is pretty important because it's more simplification you can do. You wouldn't want to leave it like this. You would want to move on a little bit more forward and just have these separate equations to work with, because this one here, it's kind of difficult to work with it on its own, and you're going to eventually go to this location anyway. So these are the 3 checkpoints we're going to try to cover in this video. Let's start off with checkpoint number 1, and I'm just going to build up to that a little bit. So I'm going to expand this, and also something I'm going to do is replace x, y, z, or another way you can write this is x plus y plus z. We're going to just call that this r vector. This r vector is a vector holding x, y, and z inside itself. Instead of writing 3 symbols, we're just going to write 1. Normally in books, they also bold this, but I'm just going to write it like so and put that little thing there, boom. So this is the Schrödinger equation in 3 dimensions. All we did was add 3 variables inside the wave function. Great. Now let's expand the Hamiltonian operator. The Hamiltonian operator is created by the kinetic energy operator and the potential energy operator, right? And since we're working 3 variables, these guys also depend on 3 variables. Let's expand this again. Kinetic energy, I remember, is 1/2 mv squared. Or if you use momentum is equal to mass times velocity, you can do momentum squared over 2m. These two things are equal. And if you remember in quantum mechanics, the momentum operator is minus I h bar partial x. But now since we're in 3 dimensions, this is going to be partial r if I'm not mistaken. So yeah, this is where the gradient or the Laplace operator comes in. So what we have here is momentum squared gives you I squared. This gives us minus h bar. Is it h bar? H bar squared, I believe, over 2m. And then here we have the gradient operator squared. This is acting on psi, and psi is a function of r. Then we have the potential energy, which is also a function of 3 variables, and this is also acting on psi, which is a function of 3 variables, and this gives us energy acting on psi, which is a function of 3 variables. Nice. So why have I done this? Well, this thing right here is the position derivative operator coming from the momentum, right? And in 3 dimensions, what this thing looks like, just a single one of these is partial x plus partial y plus partial z, right? And since we want this thing squared, this thing is considered a vector. So normally you will see a bold or with like a vector hat on top of it like this. You have to dot product this thing into itself to get the squared version. And what that means is you increase this to 2nd order partial derivatives. And in Cartesian coordinates, this looks kind of okay, like it looks pretty chill. The problem is we want to convert this to spherical coordinates. So we're going to move from psi as a function of x, y, and z to psi as a function of r, theta, and phi. So if I could draw like a little Cartesian coordinate system here, this is x, this is y, and this is z. Spherical coordinates go like this. So let me also draw the minus axes here. So starting from the origin, Z is how far from the origin, or sorry, R is how far from the origin you go. So as you increase R, you literally just grow away from the origin. Nice. This is a bit of the confusing thing. I think phi here is the azimuthal angle. I could be wrong about this, but how I remember azimuthal angle is in astrology, or no, not astrology, my bad. If you're looking at the stars and you have something right above your head, you say that is the zenith. So the thing right above you is the zenith. So when I think of azimuthal, I think of the angle zooming around the zenith. So if this is the thing pointing at the zenith, the angle, the azimuthal angle is the thing that sweeps across this thing. So in this case, that is here, we sweep across this top vector. Actually, it might be better to put Z in the top here, but it doesn't matter. You can change all these symbols anyway. So we have the azimuthal angle, which I'll draw in red, and this normally starts at X and it opens up. So I guess it'll open up. Whoops. It'll open up until it hits this guy. So this is phi. And theta is the polar angle. So this guy starts at the top axis and sweeps down all the way to here. In this case, if we want to talk about R, it'll sweep and hit that. Boom. So we have two angles. One sweeps around and tells you like which way are you facing with respect to this like azimuthal angle. Boom. This can sweep out 2 pi degrees, so 360 degrees. Boom. 2 pi radians, my bad. Then you have the polar angle, which sweeps from the top all the way to the bottom. So it's like how much vertical are you facing? So if you have these two angles, this polar one will go from the top, boom, it's either facing like right in front of you at the horizon or directly above you or like directly below you. And then the other one, the phi, the azimuthal angle, will tell you like which direction are you facing, right? Boom. So you have this one, let's say it's like the thing that you're looking at is like, I don't know, forward and to the left. This thing will tell you how high this is, and R will tell you how far away it is from you. If you like thinking about Cartesian coordinates, if you want, you can travel along the x-axis, then travel here along the z-axis, and then travel vertically until you hit the point here. So over here you have the x, over here you have the y. Oh, my bad. This is the Z, actually. I've written it a little weird. It doesn't matter. You can shift the coordinate system around. And then over here you have the Y. So 3 variables, either Cartesian coordinates, which are kind of box, cubical, very nice to visualize, or spherical coordinates, a little bit more challenging to visualize, but they give you the same information at the end of the day. And the spherical coordinates, like I said, are important. There are equations that you normally learn in calculus that relate these 2 variables. Let me see if I remember them. I could kind of like finesse them a bit here. I think this is R cosine theta sine phi. I think this is R sine theta sine phi. And I think this is R cosine phi, if I'm not mistaken. But you know what the annoying thing is? In calculus, they replace or they switch the names of the polar angle and the azimuthal angle. In physics, they flip them back. So it depends which one is which. I think if it's written the way in this picture here, and Z is facing up, so replace this as Z, replace this as X, X, Y. Yeah, call this Y, call this X, call this Z. Then this thing here, since it tells you, since the projection of this tells you how much this is onto the x-axis, the projection of this is related to this guy, I think you do flip all of these. So I'm remembering them from a calculus class, but in physics they're being a little wonky with it. Anyway, this is stuff you don't really have to remember. You could just Google it, you know, check it out. But it's a little annoying, and something important to mention that they flip it. For math, they have a specific convention. They call theta the azimuthal angle, I believe, and they call phi the polar angle. In physics, they flip it. It doesn't really matter, it's convention. Google search something or just label your coordinate system and then you'll figure it out. In this problem though, it's not too important. Maybe it's just important to know the names. But here I'm giving you like a little picture so you can see what the hell is going on. Sick. So how is this important? Well, check this out. You see how here we have x, y, and z with respect to these three variables. There's also a way of writing r, theta, and phi in terms of x, y, z. Like off the top of my head, I know r is equal to the square root of x squared plus y squared plus z squared. It's like a 3D 3D Pythagorean theorem. So you can find the distance of r by doing these guys. So this is another way of writing it. So then you can find an equation for theta and phi. It doesn't matter. But if you have these, then you can convert this entire thing into spherical coordinates. And this is actually where our first checkpoint leads us to. Here it is. I'm just gonna copy this guy, throw it down here. This is not too important, but it's not too important to derive. Maybe we'll derive it in another video because it is pretty cool, but you know, not too important for our case. So here we have the gradient operator, which I said was partial x in the x direction, right? This is the bold x hat direction, plus partial y in the y hat direction. This is a bold y hat unit vector pointing in the y direction. Partial z in the z direction. Boom. So we convert from this guy to this guy. And what is it? Well, partial r, it looks kind of the same. But then partial theta looks a little different. It's 1 over r here. Why is this happening? Probably because some conversion stuff. Jacobian, search up Jacobian of spherical coordinates, gradient operator. I don't know. And here we have another interesting thing in front of the what is this called? Phi. So yeah, boom, r sine theta. Nice. Now, why is this important? Well, we have to use this in the Schrödinger equation. So what we're going to do right now is try to compute this guy in spherical coordinates. This is the Laplace operator. It's this thing acting on itself and then that whole thing acting on the wave function. We need this because we need to plug that into the Schrödinger equation here. Once we have that, we're going to be Boolean. How do we do this though? Basically, we have, well, let's try to compute it. Partial r, and then I think it's partial r hat. Whoops, my bad. Then here I think it's 1 over r partial theta, 1 over r partial theta, plus 1 over r sine theta, partial phi, 1 over r sine theta, partial phi, phi hat. I've literally just plugged this thing into itself twice. Is this actually what it looks like? We're gonna see. Let's simplify it here. So this partial acting on itself twice gives you partial r squared, r hat component. Then we get, I guess this 1 over r combines with itself. And then this theta partial derivative is second order theta hat component. And then here we can also pull stuff out. So we have r squared sine squared theta, and then this partial squared partial phi squared phi hat. Is this true? This is where we reach our second checkpoint. And, you know, it looks chill, but something is a bit weird here. Something is a bit weird. So let's peep it. Let's check what's happening. So keep in mind what's happening here. This part right here is just from the Schrödinger equation. It's the thing coming in front of this guy, right? And then we have psi here plus v psi equals e psi. Right, so peep this. We have e psi on this side, that's chill, no problem. We have v psi right here, that's no problem, there's a plus here. And then we have this minus h bar squared over 2m minus h bar squared over 2m. That's amazing. And then here we have the Laplace operator acting on psi. So this thing here is this entire thing in brackets. And I'm trying to match it and see if it works, right? So here is one psi, psi. Here is another psi, psi, right? Here is another psi. So here, the Laplace operator is everything inside this big circle that is not these three small circles. Do you guys see what I'm talking about here? So I'm going to circle this, boom, and I want to see if this looks the same as this. So check it out. Here we have the partial. Yeah, see, it's a little weird, guys. It's a little weird because we just have partial r here, partial r, but then we have this r squared and r squared here. Like, where is this coming from? This little r squared, r squared. I'm actually not sure. Here, though, we do have an r squared, right? But then for some reason, we have a sine theta. Like, where is the sine theta coming from? It doesn't make sense. And we have a sine theta here and a sine theta here. What is going on? You know what I'm saying? And it looks like these can cancel, but they can't because this is a partial derivative of this, and this is a product rule. So some shit happens here for real. Also, it looks like these can cancel out, but that's not the case because this partial derivative is acting on this. This is a product rule. So something is going to happen here, you know what I'm saying? However, we do have one of these and one of these, and we have two of them over here. Same thing here. Check this out. Now we were missing this r squared, sine squared theta, and we have a second order derivative with respect to phi. We have that here. So a little bit of a problem. I'm not going to harp on this too much. I'm just trying to show you how I'm working through it, and clearly there's some problems here. So like I said in another video, I'm going to try to derive the Laplace operator in spherical coordinates from the Laplace operator in Cartesian coordinates. I tried my best here. I literally just dot product this thing into itself twice, plugged, like literally just did this times 2 here, boom. But that's clearly wrong because we have some extra terms over here, some extra things, some cancellations, like I'm not sure where this is coming out from. Okay, further correction, guys. I had a corrupt version of this equation here. This is actually the one quoted in our professor's notes and in the Griffith's book. Everything looks the same except over here. I mean, this looks chill, but there's an r squared missing from my version. So I forgot to write something there. And there is some other differences right here. Not too many differences. This and this combines into a full thing here. And then this derivative is acting on this derivative is acting on this. That's completely fine. And then here we have the same thing. So one tiny thing I forgot here is boom, this. So you could just forget this one and trust this one here. But still the problem persists. I don't know how to derive the Laplace operator. But that's fine. What we have here is checkpoint 2, which is the Schrödinger equation in 3 dimensions with the spherical coordinates and the spherical coordinate Laplace operator. Now what do? We have this amazing looking equation, super cool, super interesting. How do we solve it? We're going to solve it with a method that is very commonly used in partial differential equations, which is called separation of variables, which is what we did to split up the time-dependent Schrödinger equation into the time and position parts. It was very clean. Sometimes you can't do this, but normally it is the first trick that you try because it is the easiest way of solving partial differential equations. There are other methods, but this one is like just plug and chug. So what we're going to do is say we can split up the entire wave function psi, which depends on r theta phi, into 3 different parts. And these are the parts here. So what we're doing is we're saying this function, we can split it up into 3 functions which are being multiplied by themselves. This is very important. This is how separation of variables works. You separate the function into 3 different functions which are being multiplied, which each depend on their own variable. And we're calling these functions just something very simple, the capital version of the variable it represents. So psi can be split up into a component which is r, which depends only on the radial component, into a function we'll call theta, which only depends on the theta, and to a function called capital phi, which only depends on the phi variable. Why are we doing this? We will see. Now we made this kind of guess. We are guessing that the wave function can be split up into this format. So what can we do? Well, we have the differential equation here. We have the variables r, theta, and phi over here. And we have a guess. We're just going to plug this in, boom, and see what happens. Nice. So I have here, I'm going to write kind of small, 2m. Then here we have r squared 1, partial r, r squared, partial r of r, partial r. Actually, no, we can't do that. We can't do that. Actually, we can. Partial r of r, and the partial derivative acts on only the thing that depends on r. So if we act on the full wave function, this function and this function get pulled out, and only this function feels the derivative, the partial derivative. Cool. Let me know if that didn't make sense. Then we have r squared sine theta. Boom, here we have 1. Here we have partial theta. And then inside that we have sine theta. Ooh, it's going to get complicated here. Now the derivative of the wave function is acting only on theta, because it's a partial derivative. So we can pull out the r and we can pull out the phi functions. Partial theta of theta, partial theta. Cool. Now I'm going to plus, this goes here, this goes here. What do we got here? The last component. Wait a second, did I trip out here? No, I guess both of these have this r squared sine squared. Yeah, the other one has a sine theta, the other one, the third term has a sine squared theta. So this is in the denominator. Let me write that a bit more clean. Then here we're taking a derivative only on the phi components, so the r and the theta can be pulled out. I'm just writing r instead of rr, because it's easier to just write this. I'm not going to have less symbols. But I am writing the variable it depends on when I'm taking a partial derivative. I'm not sure why, I just like doing it like that. Cool, so now we have the second order partial derivative of the phi function, which I'm doing capital phi. And this is phi squared here, boom, and then big bracket close, boom, plus v acting on r, acting on theta, acting on phi, right, because we split this up, and then here e acting on r, acting on theta, theta acting on phi. Amazing. So what can we do here? Guys, I'll be real, man. What we're supposed to do is split this up so we have components that only depend on one variable. How do we do that? Well, we're going to take this entire equation up here, right? And we're going to divide both sides of the equation by r, theta, and phi. What happens there? If we divide both sides, so here we divide this by r, theta, and phi, the r here can't be canceled out because its companion r is trapped inside this partial derivative. But the theta and the phi are just functions which we can cancel here. So when we divide by this entire thing gets canceled into a 1 over r. So now this whole thing depends on r, right? There's an r here, r here, r here, r here, r here, r here. That's good. In this scenario, we divide this whole thing by r theta phi, right? The companion of the theta is stuck inside the partial derivative, so it cannot be canceled. But here we can cancel these two, like this and like this. So basically each term, we canceled the things inside here and we replace it by 1 over its companion function that is chilling in here. Right? Is that chill? Cool. I'm going to rewrite the whole equation here. I know it's probably wasting time to just write. I'm going to make my video like 6 years long. But I think it's good rewriting stuff. It makes you feel smart. Makes you feel like you're understanding stuff. So here we have r squared, 1 over r of r. I'm going to write the r of r now because it might get a bit confusing. Partial r of r, partial r. Now I'm going to do here plus r squared sine theta. This is 1. Partial theta. Here we have sine theta. Those things get canceled, and here we have 1 over theta. I guess I should write the theta pretty big. Theta of theta. Derivative of theta. Partial theta. Cool. Now we can do the next thing, plus this continues from this plus here. R squared sine squared theta, 1. Here we cancel out, what do we cancel out here? I guess we just have left 1 over phi of phi. I'm doing capital phi there. Then it's partial second order of the function phi with respect to its variable phi. Boom, close that. Boom, close this. Plus, we divide this thing also. So what we're left here with is just v. Then this equals, this is literally just e, right? Boom. Okay, looks clean, huh? Looks clean. Now, kind of an annoying thing here, though, is I think we also move the h bar squared over 2m. Because let's check our checkpoint. So what we're working towards is this checkpoint here. Let's check where the h bar squareds are. So here we have 3 different functions, which, if you notice, they only depend on their function phi here. This one only depends on theta, right? And theta's inside. And this one only depends on r. The radial function, this one here, is where we absorb the v in the e. But here we have h bar squared on the bottom and 2m on the top, when before we had h bar squared on the top and 2m. So this is suggesting that we divide out by this thing. And do we have an h bar squared anywhere else? We don't actually, bro. Huh. Very interesting. Let's peep. Maybe we should also copy these guys over, huh? But I can't copy them all at the same time. Let's check our equation. So if I divide both sides, let's assume I divide the entire equation by minus h bar squared over 2m. What happens there? If I divide that, then here this thing gets canceled from the entire thing of the brackets. So then it brings it here and it brings it here. Oh, that's not bad actually. That's not bad. Okay, we're actually going to do that. Divide both sides by that. So it's going to cancel it here, right? And what we have here, I'm also going to erase. If we divide v by h bar squared, minus h bar squared actually, this thing becomes minus v. There's a 2m at the top and there's a h bar squared here, equals minus e 2m h bar squared. So a little bit of a modification. We divided that whole equation by this just to reach our checkpoint a little better. All right, we're at 35 minutes. I'll be real with you guys. I will be real. Can we even split this up? Can we split this up? Okay, I'll tell you what we're gonna do. I will tell you guys. Peep this. We have a big bracket here. We have one term plus a second term plus a third term. That's all we have inside these brackets. So basically we have big brackets with 3 terms inside. Here we have a constant. V is a constant. It's actually a function, but it's a function, huh? Damn. Yeah, I think we should combine the V and the E. I'm saying we should combine this and this together and couple it with this guy here. Okay, I'm going to draw very, very small here so that we can see everything on one line, because I think it's going to be good. Partial r, then here we have r squared, capital R, on the bottom here, partial capital R, partial r. Um, we remove those big brackets, and then move that e. It's going to be plus e. So we have a minus, minus 2m over h bar squared. And then, I think we should do a plus, because then if we move that, boom. I'm just thinking how we should combine this. Let's check our checkpoint one more time. Check out what's happening here. 2m, there's an r squared which we put there, which we could do as well, h bar. Here we have a v, here we have a ve, and then this r is being multiplied there, huh? What's going on here, boys? What's going on here? V minus e, and then there's a minus sign here. V minus e, v minus e, v minus e. Remember v minus e. So it's minus here. We subtract, and then we have v minus e. And also, we FOIL over this r. But we can't do that right now, boys. Can't do that shit. Because this derivative. Look, I'm basically trying to explain myself. We have an r here and an r here. I'll multiply both sides by r. There's this partial derivative which is fucking us right now. Okay, anyway, what I did is I take this, right? I'm gonna bring this to there. It's okay because we just have one term plus another term plus another term minus another term plus another term. I'll move this here, then this side is gonna be 0. Alright? We got 2m h bar, 2m h bar. Pull those out, leave those inside brackets like this. Minus v, minus v. This e is a minus, it comes on this side, plus plus, it's going to be a plus. But since we have a minus here, this minus and this is going to be a plus, and this is going to be a minus, all right? So peep this, minus v, and then minus minus e is going to be plus e. So we have minus v plus e. Minus v, move this here, plus e. Boom, and we have its factors over here in the front. I gotta speed up a little bit. And then we close brackets. Actually, no, we can't close brackets there. We have to close brackets here, minus, and then that thing. Yeah, we can't close, we have to close brackets here because this thing is acting on this whole thing. This thing should not be acting on this stuff. It's fine if it, actually it's not fine if it does. Because v depends on r. V is a function of r. We're assuming v is spherically symmetric. Anyway, we're going to move on here to the second term, which we can say is r squared sine theta. Can I put this all in one line, boys? Actually, maybe I should make this smaller. V minus e. V minus e. Yeah, that's going to save a lot of room. Then here we have partial with respect to theta. We have a sine theta. We have a theta function on the bottom. 1 theta, theta, partial theta. Give me the last term. Plus r squared sine squared theta 1. Here we have, or theta, yeah. Here we have a phi function. Oops. This is a phi. 1 partial squared phi. I'm gonna, fuck it, I'm gonna put this here, boom. Partial phi squared, close brackets. Okay, now you know what? What I'm gonna do? I'm gonna actually make this a bit smaller so I can finish the equation. Resize this bad boy, boom. Equals 0. Okay, here's what we did, guys. This term here, we kept over here, and we just brought in this term and this term next to it, because it's going to be part of one function. This term we kept exactly the same. This final term we kept here. Since we moved this e into here, it equals 0. Okay, what are we doing here? Check out what we have. This entire block right here, v depends on r. We're saying v depends on r only, and v does not depend on theta and phi because we're going to say that V is spherically symmetric. So it doesn't matter which location you look at, there is no dependence of V on these things. Perhaps there will be, but for the hydrogen atom, there won't be. So we couple this with the R. This is the only thing that depends on R here, right? And then we have R here, R here, R here, R here, R here, R here. So this entire glob right here, this entire thing right here only depends on R. Nice. Now the thing about this part is it only depends on theta, and the final part here only depends on phi. Keep this. We have a phi here, we have a phi here. Oh shit, we have a theta here. No, this is not going to work, guys. This is not going to work. We have to multiply everything by theta squared or something like that. Then we're going to have thetas everywhere. Ah, I see what's going on. So these parts only depend on phi and theta, while this part only depends on r. So if that's the case, the problem here is separation of variables needs different sections that only depend on one variable. So what we have here is a split between something that depends on r and a split between some big chunk that depends on theta and phi. And this equals 0. So check this out. This depends on r. This depends on theta, phi. What we're saying here is that a sum of differential equations that depend on different variables equals 0. There's no chance this can be true because if I move this onto this side, it's just going to slap on a minus sign. So I have a differential equation with respect to r, or a full equation with respect to r, equals an equation with respect to theta and phi. They don't depend on each other. So if they don't depend on each other, I can change one of them and keep the other one constant, which breaks the inequality. If I change something about r and keep the theta the same, or the other way around, if I change something about phi and theta and keep the r one the same, the equality breaks. So the only way this can be true, and this is the crazy thing about separation of variables, is both of these things have to equal each other, and the only time that happens is if they equal a constant, because then I can change one of them, it's going to equal a constant, and I can change the other one, and it's still going to equal the same constant, so the equality is not broken. Amazing. So what that means is we can split this up into two equations. One of them is going to be this one, 1 over r squared, partial r. Then here we have r squared, r, the function r on the bottom, and then partial r, the function with respect to r, minus this, 2m h bar squared. Then here we have v minus e. By the way, the v depends on r, so maybe we should write that, minus e. This is equal to, what does it equal? They call it a constant, but they actually call it a very special constant. They call it L plus 1. You can call it any constant you want, but I think this is what they call it. Let's check our checkpoint. Let's copy this guy actually. Paste it here. Is this true? No, looks different, huh? But I guess, here's the problem, guys. Check in here. We have an 1 over r squared, 1 over r squared, 1 over r squared in each of the terms, and no r squared here. So if we multiply this whole thing by r squared, check this. It cancels this one. Check this, it cancels this one. It adds an r squared here, and it cancels this one. So what we can say is we'll erase this, right? Then here we will add a 2m r squared. This looks like it's chilling. It's looking a little better. And, but still, I don't feel comfortable about multiplying through by this one. Because now if we take this whole equation and multiply by r, right, it's going to slap on an r over here, which is seen right here, and it's going to slap on an r over here, which is seen here. So perhaps when I divided originally by this, I should have had it on the outside, because I can't remove it from this because it's trapped by the derivative here. So perhaps that's a mistake, but I'm going to just take that, move it over, take this, move that over here, and leave some room for an r. We have an r and an r. And this is our first checkpoint. Actually, I'm going to leave this circle here. Circle this with a big thing. Why is this cool? We have separated the three-dimensional Schrödinger equation into something that only depends on r. Now it can work only on this equation. It's going to be much easier than also working with thetas and phis. Now let's go back to the original thing. We've modified, manipulated the Schrödinger equation into this. This still is containing information about the Schrödinger equation. We've done nothing wrong to it. What we're going to do is take this, which depends on theta and phi, and we're going to say this whole thing is equal to this constant, which we said before. Right? This constant is coming from the separation of variables thing, and we're just calling it L plus 1, instead of calling it E, instead of calling it C, instead of calling it some random constant, because in the future L and L plus 1 is going to be a very valuable constant. If you remember when we did separation of variables with the time-dependent Schrödinger equation and we got to the time-independent Schrödinger equation, the separation constant we called E. Why do we call it E? Because the separation constant told us information about energy. But we didn't know this until later when we saw it was related to energy. So this thing is labeled this way by first labeling it something random. Let's label it K. Later we see, hold up, this K actually has information about the angular momentum, if I'm not mistaken. I need to read a little bit more to see this. But anyway, we're gonna leave it at that. So let's copy this with a little orange color here. What we have is 1 over, we got rid of this r, huh? We got rid of this r. Here is theta. Here we have sine theta. This I think is wrong, this part that I'm writing right here, but we'll see. Partial theta of theta plus sine squared theta. We got rid of the r squared from before, remember? Here we have a phi, 1 over phi, and a second derivative of the phi function with respect to phi. This equals L plus 1. Are we good? We're not good yet. We want to separate this again, use separation of variables, but the problem is, here we have something that depends on phis, and here we have theta. Here we have thetas, huh? Multiply this out. Let's check, I think the phi equation is going to be a bit easier. Okay. Yes, this makes sense, guys. This makes sense. Okay. We're actually swimming. We are actually swimming here. Boom. Now check this out. What we're going to do is first multiply both sides by theta. Multiply both sides by sine squared of theta. If we do that, the sine squared of theta cancels here. There's a sine squared theta here, and what it looks like is this original theta cancels with this one, which I still don't understand how, because it's trapped by this. But, oh no, it doesn't cancel with that. Does it? Did I forget something? 1 over sine squared theta. Oh, I did forget something. Yes, my bad, guys. I did forget something crucial. So a little mistake on my part, but it's not a big mistake, it's just me forgetting to write something. Boom. There is actually, go back in this orange, sine of theta over here. Check out how I missed this. Sine of theta here, sine of theta here. Now, if we multiply both sides by sine squared theta, we're going to slap a sine squared theta onto this L plus 1 term, which is visible over here. It's slapped onto this L plus 1 term. And here we have a sine this, we have a sine this. This guy needs to get out of there. And this thing, after you multiply by sine squared theta, one of these cancels with one of these, and we just leave with this here. And this thing gets pulled out to the front. It doesn't get pulled out to the front, again, because it's trapped by this derivative, but I think originally when I divided both sides by this, I was not allowed to do it here. It still feels a bit weird though, guys. I'll be real with you. Anyway, we're just going to follow, even though there's some mistakes. This is what math is about. So what are we left with? Sine squared theta. This sine squared theta actually cancels with the other one. And then here we have partial theta. Oh, but now we have full derivatives, guys. And here we have full derivatives too. Because we only have a derivative with respect to one thing. Nice. And then here we have the original sine theta, derivative of the full theta function, which I'm going to write like this, d theta, plus. But why is it a plus? Shouldn't be a minus there? Ah, yes, this is the thing. When we said that this thing equals a constant and this thing equals a constant, they equal this constant, but when you move this to the other side, it slaps on a minus sign. So here there should be actually a minus, and then when you move it over to this side, it becomes a plus. So I'll just leave that as is. Sine squared theta. Now we can separate this. So we've separated this part, only the thetas. We got rid of this, so this thing and this thing are functions of theta and phi. And we can do the same thing, separation of variables. I can turn the theta bar while keeping the phi, turn the theta knob while keeping the phi one constant. This doesn't work because the inequality breaks, so the only way this could be true is if they equal a constant. Okay, and what do we call this constant? We'll call this constant m squared with you know, random foresight of solving this problem. We'll just call it m squared to proceed with the quantum workflow. But if you're a mathematician solving this, you could call this constant anything. And one other thing I'm missing here is there is actually a theta function here, like that. So it gets pulled out from there. Nice. So that leaves us with one other thing, which is, actually I'm going to circle this and then circle this. That's one of the checkpoints. And then the final one is going to be this guy over 1, second order derivative of this is equal to just a constant, but it's going to be minus m squared. Same reason as before as why we had the minus. And this, I think, is the most simple equation, which we can all solve together. And it is this one. Copy. Nice. Circle this. Circle this. So what do we have here? We have the final checkpoint, which is the 3 different differential equations. I'm going to stop here because the video is very long. Solving these on their own is very crazy. You can solve the green one. It's okay. Use some standard differential equation solving techniques. The orange one is very, very hard to solve. I don't know who can do it. We're just going to look at some solution online. The pink one you cannot solve unless you tell us what V is. And we're going to look at V, which is the potential around a hydrogen atom, which is the Coulomb potential. So, in summary, what we did was we started off with the one-dimensional Schrödinger equation. We said, okay, we can move from the time-dependent Schrödinger equation to the time-independent Schrödinger equation using separation of variables. The separation constant is E, with you know, hindsight that this E represents the energy. But separation of variables here is very important. And by the way, they separate this function, they separate this function x of t into two functions, squiggly psi of x and phi of t. This is the separation of variables, moving from the time-dependent Schrödinger equation to the time-independent Schrödinger equation in one dimension. You could do the same thing in three dimensions. However, we start from the time-independent Schrödinger equation in three dimensions. We saw that we have to add these three dimensions. Then we expand the Hamiltonian, and we see that the Hamiltonian includes the Laplace operator, this, which looks like this. Sorry, the gradient operator looks like this in Cartesian coordinates. The Laplace operator looks like this. This is just the gradient, and the Laplace is what you call the gradient operator squared, or the gradient operator acting on itself, acting on something. So in Cartesian coordinates, this is this. But then we moved on to spherical coordinates. And in spherical coordinates, there was some problem. How do you define, or how do you derive the gradient operator from Cartesian coordinates to spherical coordinates? This is a little bit confusing to me. And how do you derive the Laplace operator in spherical coordinates? This is also kind of confusing to me. I'm going to study this on my own. I'll give you guys some information if I find any. Then what we do is we manipulate the equation. So we plug in separation of variables, which is a guess, which says the function can be broken up into a multiplication of three different functions, each depending on its own variable. Then we manipulate the equation and we end up with three different equations, each of them depending on their own. This one depends on r only. We also have a v there. This one depends on theta only. So this is the final differential equation. And this one depends on phi only. And we introduce two new quantum numbers in the process, which came from the separation constant in separation of variables. The first one is this L. What is it? We don't know. We're going to figure out later. And the next one is this M. What is it? We also don't know. We're going to figure out later. Anyway, I hope this was helpful to you guys. I know it's kind of complicated, but try this out on your own. You don't have to really do much mathematics. You kind of just have to rewrite the equation and manipulate it a couple times. If you're confused how you get the gradient operator, you can just search up on Google gradient operator or Laplace operator in spherical coordinates. What is it? Boom, you'll get it. No stress. Plug that in. You're not going to be asked on a test or something, derive the gradient operator. This is stuff for a math class. So I hope this was helpful. In the next video, we're going to look at just the solutions to these guys, which are super cool. They are called the spherical harmonics. This is a set of functions that are super cool. If you plug these functions into these differential equations, or the differential equation that combined both of these, they are solutions, and they're super cool. And they actually give you information about orbitals of atoms, which you see in chemistry class. So we're going to peep that out. We're going to talk about those very quick. And then maybe we're going to take a look at this radial equation in the future. So I hope you guys enjoyed. I will see you guys in the next video. Thank you guys for watching. Sorry it was a crazy one. Let me know if you have any questions. And yeah, suggestions for future videos. I got you guys. Peace.